Good morning, students. Today we shall see flat belt design. Yesterday we have seen introduction about the flat belt and its types. Today we shall see about the design of flat belt system. And before going into design directly, we shall know advantages of flat belts and disadvantages of flat belts. First, let us take advantages of flat belts. The efficiency is 98%, which is equal to that of gears. Second point, high load carrying capacity. Third point, can be employed where high operating speed is required. Fourth point, they produce less noise compared to V belts. Fifth point, they can absorb shock loads compared to V belts. Though many advantages are there, there are some disadvantages of flat belts also. First one, flat belts cannot be operated on smaller diameters pulleys. Second one, if the working environment is corroding, the belt life decreases. Next, arc of contact. This is very important while designing. It is nothing but the angle subtended by the belt of the pulley is known as angle of contact or arc of contact. For better performance, the angle of contact should be between 90 degree to 170 degree. To increase the angle of contact, idler pulleys can be used. Next, let us see flat belt selection using PSG design data book. For the calculation of a two pulley power transmission belt, the following data are required. First one, we should be known about the motor power or power to be transmitted in kilowatt. Second one, speed of drives. There are two speeds. Driver now speed or revolution of number of revolutions of driver pulley and driven pulley, small n and capital N. Diameter of the pulley, diameter of the driving pulley small d, diameter of the driven pulley capital D. Transmission ratio or velocity ratio I. It should be always greater than 1. Center distance C. Next, procedure stages. First point, selection of standard pulleys. Second point, design power calculation. Third point, selection of belt. Fourth point, calculating load rating and required number of plies. Fifth point, selecting belt width. Sixth point, calculating length of the belt. Seventh point, pulley dimensions with number of arms, crowning, etc. Let us see one problem. A belt is to transmit 20 kilowatt at 720 rpm to a rolling machine with a speed ratio of 3. Center distance between the pulleys is 3 meter. Design a suitable belt drive if the rolling machine pulley diameter is 1.2 meter. First, list out given data. Power is given as 20 kilowatt. Driver speed small n equal to 720 rpm. Transmission ratio I equal to 3. Center distance C equal to 3 meter. Driven pulley diameter capital D equal to 1.2 meter. Next, we have to find diameter of smaller pulley, since diameter of larger pulley is known and velocity ratio is also known by using formula I equal to D by D into small n by capital N. We can know the speed of the smaller pulley. Step 1, selection of standard pulleys. After finding the speed of smaller pulley, we have to check the size of the diameter of the pulley, whether it is standard one or not. Page number 7.54, standard pulley diameters are given under the table. The table name is recommended series of pulley dimensions and tolerances. For our case, diameter equal to 400 mm. So for 400 mm, tolerance is plus or minus 4 mm given. Similarly, for larger pulley, diameter equal to 1200 mm, whether checking that 1250 is available and with the tolerance of 8 mm. Next, step 2, design power calculation. Here one formula is there. Design power equal to rated kilowatt into load correction factor upon arc of contact factor into smaller pulley factor. This formula is not available, so we have to memorize it. For finding the design power, first find load correction factor. It is given page number PSG design data, page number 7.53. For our case, that is for our problem is it is for rolling machine. We have to design belt for rolling machine. So we have to refer in page number 7.53 in the table load classification, load correction factor, etc. In the load classification, we have to check whether rolling mill is available. Yes, available. And then under the column of load correction factor, if we search it, we can find 1.5. So load is sock load for rolling mills. So load correction factor equal to 1.5. This data is available in PSG design data, page number 7.53. Next, we have to find arc of contact. The formula is arc of contact equal to 180 degree minus capital D minus small d by C into 60 degree. Here capital D is diameter of larger pulley, small d equal to diameter of smaller pulley, C equal to center distance. Page number 7.54, arc of contact factor is given, correction factor is given. Here for our case, arc of contact equal to 180 degree minus 1200 minus 400 upon 3000 into 60 degree. So arc of contact equal to 164 degree. Corresponding to the 164 degree, this is not available. So either we can take average of 160 degree and 170 degree values, or we can interpolate it. So I have taken nearby value. So nearby one is 170, so 1.04 I have taken as arc of contact factor. Next, from page number 7.62, smaller pulley diameter factor is available. For our velocity ratio or transmission ratio I equal to 3, it is given as 1.14. Small table is available in page number 7.62. The table name is speed ratio range d by d into and smaller diameter factor FB. Next, we have to substitute all the data we have found that are taken from the design data. So design power equal to 20 rated kilowatt. It is given in the problem as 20 into load correction factor 1.5 divided by arc of contact factor 1.04 and smaller pulley diameter factor 1.14. When you calculate it, we are getting 25 kilowatt as design power. Next, step 3. In page number 7.52 of the PSG design data, we can see two types of belts have been given. One is Dunlop high speed 878 grams per square meter It is for light and medium duty purposes. And another one, Dunlop Fort 949 grams per square meter fabric belting is given. It is mainly recommended for heavy duty and for medium belt speed applications. Next, step 4, load rating and number of belt plies. For that, we need to find velocity of the belt. Page number 7.54, velocity of the belt formula is available. V equal to pi dn by 60. Here d is the diameter of smaller pulley and n is the speed of the smaller pulley. So when you substitute values, we are getting 15.08 meter per second. Then in page number 7.54, load rating per mm with per ply at 180 degree arc of contact at 10 meter, standard 10 meter per second belt speed. They have calculated and given a formula. And for our velocity, the same 10 meter per second belt speed to be used for our purpose multiplied by our multiple times of portions of 10 to be multiplied. So load rating equal to 0.289 into 15.08 divided by 10. So load rating we are equal to 0.04358 kilowatt per millimeter per ply we are getting. Then from page number 7.52, based on the values of velocity and the diameter of the smaller pulley, number of plies are found. In the table, in the top side, from the top headlines, minimum belt speed meter per second. So in the table, we have to search velocity 15.08. So 15 is available, and under the column of 15, we have to search 400 mm diameter, but 400 mm is not available. Then we have to search nearer value. 315 is nearer value. Corresponding to 315, 6 ply belt is there. So we have decided 6 ply. Next, step 5, selection of standard belt width. The formula is given as width of the pulley equal to design power into load rating into number of plies. Page number 7.52, one table is there. And width of the pulley equal to 25 design power, load rating 0.04358 and number of plies 6. So width of the pulley we are getting 95.60. Then next, from page number 7.52, there is a table corresponding to 3 ply, 4 ply, 5 ply, 6 ply, 8 ply belts, and under that 6 ply we have to search width of the belt for corresponding to 95. So next number is 112. It is available with a single star mark. Single star mark means belts of both the varieties are available, so we can choose that one. So standard width of the belt equal to 112 mm. Next, step 6, calculation of belt length. From page number 7.53, for open belt drive, L equal to 2C plus 5 by 2 into D plus D plus D minus D whole square divided by 4C. This formula is given. Similar to this for cross belt drive and quarter ton drive, belt length formula is given. For our case, for open belt drive, length of the belt equal to 2 into 3000 plus 5 by 2 into 1200 plus 400 plus 1200 plus 400 whole square divided by 4 into 3000. That will be equal to 8566.6 mm. Next, pulley dimensions. Width of the pulley equal to pulley From page number 7.54, pulley width equal to 112 mm plus 13 mm, that is equal to 125 mm. In page number 7.55, one small table is there, and corresponding to the belt width, pulley sizes to be wider than the belt. So how much wider it is given? Yeah, up to and including 125 mm, 13 mm should be wider than the belt size. Belt width. So pulley width equal to 112 and extra size 13 to be added, so 125 mm. So next we have to check whether standard pulley with 125 mm is available or not. In design data book we are checking and 125 is available. Next, number of arms. 4 for diameters up to 450 mm and 6 for diameters over 450 mm. From page number 7.56, for smaller pulley 4 arms and for larger pulley 6 arms. Then crowning of the belt. For smaller pulley, diameter equal to 400 mm, pulley width equal to 125 mm. Corresponding to these two values, we have to find height of the pulley should be height at middle of the pulley, that is crowning. So in this case, for 400 mm and 125 mm, h equal to 1. And similarly for larger pulley, for d equal to 1200 mm and pulley width equal to 125 mm, h equal to 1.2 mm is given. Thank you.